everyone. I'm here to present you a work with Seth Gilbert from the University of Singapore and Vincent Gramoli from the University of Sydney. So it's about accountability. So I will introduce the issue. So we have n processes who want to solve the consensus. So there are some primitives like send and receive messages on reliable communication network, point to point. The guys can sign their messages and broadcast them. And we are under partial synchrony. So under partial synchrony, we can't assume the fact that a message arrives after a certain time. So you can't encode a certain bound of the arrival of each messages. So that's why you can't make the difference between somebody who is very, very low and a Byzantine node who don't want to send a message. So we have the signature, so we are already seeing this, those primitives. And we are playing with Byzantine processes. So the Byzantine processes can produce some different type of faults. You have omission, so you don't send the message that you're supposed to send. And of course, the correct guys cannot make the difference between we are on under a partial synchrony assumption. And there are commission faults. So commission fault is about sending a message that you're not supposed to send. And in commission faults, you can see another type of faults, which is called mutant messages. So it's when you send two different messages to two correct nodes in a time where you're supposed to send the same message. So I introduced that because there is this different type of nodes. Of faults, and there are someone who are more easy to detect than the other one. So in a formal way, we call about observable faults. So the mutant messages are quite easy to detect if you are able to make the concatenation of two signed messages with the same header. So when I'm saying the same header, I mean you're supposed to send the same messages at the same time, but it's not the case. So here, Dave wanted to send two different messages to Alice and Bob, and after a certain time, when the network is established between Alice and Bob, they can concatenate their messages and build the proof that Dave sent mutant messages. So it was for the topic about the faults. Okay, here we have some Byzantine nodes with a certain power, but we assume that he is not able to forge a signature. So it was about the model, so we are assuming to play a game with some Byzantine nodes who can practice some type of faults, the commission faults, the omission faults, and more precisely the mutant messages. And the question is it possible to solve the consensus? And there are, so I guess we already know what is the consensus. So you have initial values, and you want to decide on the same value, and you want to solve the liveness, the agreement, and the validity. And thanks to the solution of this problem, you can build a blockchain when you eventually decide on blocks with a certain property. So it's pretty cool, but we know that under those assumptions, so particularly under partial synchrony, we're not able to solve the consensus when the number of malicious players is greater than n over 3. So the first question that we could ask is it possible to preserve the safety properties even if t is greater than n over 3? So that is, you want to solve the consensus in the good scenario when t is lower than n over 3, but you want to preserve the safety property, and maybe you can tackle the liveness. And in fact, it's not possible. So I would like to show you really quickly the demonstration. So it's about undistinguishable scenarios. So here the word is split in three parts. We have Q, P, and R. And basically, Q could be malicious, but not every time. And sometimes P and R can crash, but not at every time. And as I said, when T is lower than n over 3, we want that everybody eventually decide. So in the scenario A, we have T which is lower than n over 3. Here, all the members of R crash. And that's why everybody is supposed to decide. So if you are a member of P and everybody started the challenge with the value 0, for example, here green, eventually you're supposed to decide because you want to solve the consensus even if T is lower than n over 3. You have the same thing in the scenario B. So here, if all the members of P crash at the beginning and everybody started with the value red or 1, you want to decide. So because T is lower than n over 3, so you want to conserve the liveness property. So here, R is supposed to decide red. And in fact, there is a third scenario, which is undistinguishable for P and R, where the speed out of the network is very low between P and R, and Q is malicious. And here, Q just acts as in the same as in the scenario A with P, and as in the scenario B with R. And because, for example, for the point of view of P, you don't know anything about R, so okay, you have enough messages, you're supposed to decide, because in the case where R crash, you want to decide. And that's why you're not able to preserve the safety properties when T is greater than n over 3. So okay, since we have seen that, what one can do? What is able to do? And we propose the accountability. So basically, the idea is say, okay, it's impossible to solve the consensus when T is greater than n over 3, but we would like something like, in the case there is a disagreement, we are able eventually to detect who is the author of the malicious attack. So there are already some literature about this problem with, for example, unreliable failure detector with peer review. But usually it's quite difficult to have a satisfying overhead. So here we want to just don't produce an overhead of message complexity to ensure the accountability property. And we want to bound the bit complexity to ensure the same property. So that's the idea. When you are under the classical bound, you still solve the consensus, so safety plus liveness. And when T is greater than n over 3, in case of disagreement, you have always deduction. That's not about slashing for a certain subtype of faults. If, regardless the technique, you always have the deduction of n over 3 malicious players in case of disagreement. So of course it happens eventually. So the intuition is to say, okay, P and R collect some proof, and when the network is reestablished, they can exchange the proof and make the good concatenation of signed messages to have a proof of culpability, as I showed you with Dave before. But in fact, it could appear some trivial because you just have to collect these messages, and okay, it's easy. But the challenge is about unobservable faults. So the idea is to say that, in fact, if you are a big malicious coalition, you're not obliged to tackle the safety properties with mutant messages. In fact, it's possible to tackle it with commission. So when you flip the value, so usually you have an estimate value that you consider to decide. Here it's green or red. and you're running during some rounds, and eventually you're supposed to decide. And the idea is that, in fact, usually you can tackle the safety property with just commission, with just flip. And so the challenge is to transform non-observable faults to observable faults, but with a bounded overhead. So, okay, you can, for every type of consensus, you can go to binary reduction. So you just go to a binary consensus, so it's not important. But the idea is if you solve the binary Byzantine consensus, you can solve the Byzantine consensus. And there is an intuition about the fact that you can't avoid the fact that two correct processes could decide in two different rounds, and that's why they are unobservable faults. And so the idea is just to transform the messages with some justification, but you don't want to do a naive justification. So a naive justification is about put all the history of what you received to justify a certain value. And of course, it's okay. You could imagine that in certain one, when Alice proposed an estimate value, she could just sign all the messages that she received to legitimate her proposal. But there will be a very high bit complexity. So that's why you're supposed to design your consensus protocol to be able to build a bounded justification. So in our results, we were able to have a bounded justification, and because of that, we're able to have an overhead which is bounded. So just O of n bit complexity. And that's the result. So if I want to conclude, what you have to retain is that there are two types of faults: the ones who are observable and the ones who are not unobservable. It's not a trivial thing to transform a non-observable fault to an observable one. And I guess you're supposed to add some justification with certificate, with some signatures, to transform the unobservable faults to observable faults. And this transformation has a certain cost. And we would like to have the lower cost that we could, but probably there is a bound of this cost. So we reach the bound of O of n bit complexity, and I conjecture that it's not possible to do better.